gather people, technology like-minded people in the Coimbatore area and have a knowledge sharing over weekends. So just to present, come and present what is happening in the industry, understand, collaborate each other with the business and the technical networking. So first, before getting into quantum circuit programming, understand what are the foundations of quantum computing. Why did we go for quantum computing, right? So what are the core principles? If you look at the classical computers, where computers are nothing but underlying it has all the circuits, PCBs, and everything, but it definitely we understand either zero or one, right? So those are signals are like power in the circuits where it can understand either zero on or off. That's when it actually find out what are the tasks that we give to it. So it converts into the machine understanding formats of zero and one, either and it's all also like operations are so deterministic, mostly like mathematics involved, right? So and also it's all predictable based on whatever the data that we feed in. And it actually scales linearly based on the problem complexity. For example, if we write a program, right, every programming language starts with the hello world, and we write a complex multi-parallel operations as well, right? So nowadays, if you look at, we have CPUs and GPUs, like central processing unit, which will have its own processing capacity. So we can assign, if it's a single core processor, we can run one process at a time without any interruption. If you run multitasking, so three or four processes at the same point, it will not be able to give a same speed as the single. It has to queue it, queue it in a bit. So if you run a multi-core processor, where now we see Intel i5, i7, so or x86. So there we have a multi-core processor, like four quad cores or octa cores, 8 cores. Then we can run based on the processing capacity. It has its own memory and everything. So that's when it scales linearly. When we run a parallel operation, if we want to run more parallel operation, we have to throw more hardware, right? More processing power to process it, right? Based on the complexity. And it is perfect for everyday computing operation. Like we want to run some any machine learning algorithms or some like a regular business functions, like we have all the mobile app or the web application and all those things, right? So where we can just test 1 million password sequentially, it takes 1 million operations. So if you're asked to throw a login page, and we sign in after our signing up. So if you want to test for 1 million password, whether it is it's a right password or not, so it takes 1 million times it has to verify. This is the classical. So it's more sequential and little bit of parallelism. But why we need quantum computing? Because it actually apart from, so the people thought, why can't we go with more than two, right? Only everything is like zero or one. So what are the other possibilities? How can we parallelize and increase the computing power, have a simultaneous paths? So that's where this quantum came in. But still, we are not changing the number of bits here. So we'll just say zero and one only. But they introduce a concept called qubits. So we will see what that is. So there is an intermediate state between 0 and 1. So it's not like mathematically measurable, like 0.1, 0.2, 0.3, as in a straightforward way. So that's when, based on these conditions of different probabilities between 0 and 1, how it can actually do different states, and how can we speed up the things in the different states, right? For example, it can search the same password space dramatically faster than using the quantum parallelism. So instead of doing 1 million password in 1 million operation, it can do it in few times, like in less than 5 or something. That much fast it is. So let's understand what are these concepts. We talked about the qubits. Instead of bits, right, 0 and 1 in the classical computing, qubits is used in the quantum computing fundamental. So there are multiple the states, right? So first, one of the concept that we need to understand is superposition. So where the qubits exist in a multiple states. For example, we have 0 and 1. So it will be this need not to be only two qubits, right? So with qubit 1 is like 0 and 1. There is another qubit which can also be either 0 or 1 state. Similarly, we can have multiple qubits for a parallel operation. So if you have multiple qubits, then the combination would represent like 2 to the power of n states. So if you take a quick example, right? So if you take a coin, two sides of a coin, it's either a head or a tail, right? It's assume that 0 or a 1. If we have it in our hand, we can either see one side of it, so it will be either 0 or 1. But if we spin the coin, then there will be n number of probabilities whether it can be in any state, right? So once it falls down, so probably it has to be in either 0 or 1 state, or head or tail. But while spinning, so we can see we cannot predict which is going to be the head or tail, right? So that's the number of states that it has. So each of those states while spinning is called the superposition. And entanglement is another concept we need to understand. So since we have the qubits, so each of the bit have multiple states, right? That's what superposition is. In whatever state it is in, between the 0 and 1, in any other direction, right? So this entanglement is we'll have multiple qubits, right? So we talked about it can have n number of qubits. So the relationship between each of these qubits, right? What they're saying is, so the qubits can be somehow it's actually correlated in a base. So that's what I just wanted to connect this with a simple example of quantum physics, right? So I'm not sure how many of you believe in this theory, but so what I strongly felt when we had a COVID right, so a couple of years back. So we had multiple waves. So it was a new phenomenon that the human body couldn't produce antibodies initially because it has to learn for the virus that it gets into human body. But in the second wave, I mean, though we have these vaccinations and everything, it actually developed itself some immune and some sort of additional antibodies to prevent from it, right? So at least in the second and third waves, so because of if one person is able to develop immune from it, so every humans are interconnected, right? So it learns itself, so it actually passes without like that. That's where the quantum physics comes in. So where it passes the information, so it actually learns itself and started developing. So of course there are multiple factors affects how the other person's immune is and the way where they are living and other history of all the history of all their disease and everything. But still, it's all every particle in this universe are interconnected, right? So that's the same concept where we have the qubit. The entanglement is like where if it one changes, it indirectly affects the other similar one, irrespective of wherever it is. So even in the example, what they're saying is in the quantum physics. So if we have a molecule in Earth or in this in this solar system, so if it's the same kind of one is available in any other solar system, both if the changes are there, it automatically detects that, right? So that's a level that they're saying. So Einstein researched this theory and they call it as a spooky action. And I think we saw about qubit, it's a fundamental unit of a quantum information. So this includes the superconducting circuits, ions, photons, and everything. So the low-level particles, right? And which is incredibly fragile and extreme conditions to maintain the quantum properties. So that's to have it either 0 or 1. So now we talked about quantum computing with these states, but what is quantum circuits? So basically, in the legacy or the classic computer world, so we've actually learned about all the physical logical operations, right? So logical gates. So those are the operations happens between the bits, right? So if you have a 0 and 1 or 0 0, all are 2 to the power of 2 combinations. We have the gates like AND, OR, NOT, XOR. So those are the different gates that we read. So what the logical perform logical operation in the bit, but in the qubit side, so they also have a concept called quantum gates. That again, this is these actually manipulate the states through like your unitary in transformations, creating complex quantum operations. Again, the gates are really helping to perform the operations in the qubit. And why quantum circuits? They provide a programming language. So we have to provide some programming language, right? So like which should be human understandable, and at the same time that converts into whatever the quantum machines can process it. So that's where the quantum circuits are like a programming language for quantum algorithm. So really helps us to use the quantum mechanical phenomena, implement that. So well, let's talk about quantum gate. What are those? Right, similar to the AND right or NOT gate in the classical computing. So here also they have X NOT. So which actually flips the qubit state. So whatever state it is in, it will simply provide an opposite direction. If it's like zero or some state there in between, so it'll actually flip that to the inverse of it. And this is like this is like clearly quantum equivalent of classical NOT gate. And Hadamard is another second state where it creates a superposition by transforming the zero into equal probability of the closest one. So whatever this converting, it's actually taking it to the next level. Right, this is most important for the parallelism. So when we run the parallel operation, so this really helps us to find out finding out the equal probability. So finding out in the quicker fashion. And there are multiple phased gates. So when there is a atom or electron, the lowest level of in the quantum bit, right? So assume that which will have a three-dimensional, right? So three direction, which will have the position that it is in. So which actually helps to rotate the qubit space without changing the measurement probability. So you just this is just to make sure that out of this 0 and 1, which is moving in one direction, either it's up or down or sideways, whatever dimension that it is running. So it really helps to change the pace without changing the measurement probabilities. So this really helps for in the quantum algorithm. So which is really useful for the machine learning, implementing the machine learning models here. And finally, there is the concept called C0 gate, which is like 2-qubit control gate. The other ones are mostly like a single, but here it's a 2-qubit control gate, which flips the target qubit. If controls is 1, then this is really helpful for these entanglement, because we saw earlier. So the entanglement is the relationship between the two qubits at any respective the distance. So this creates entanglement and universal for quantum computation. So this is also important now in the quantum set. So we saw the superposition, which is like always superposition as we see spin of the coin, which gives a 50% probability. The entanglement is non-local correlation. And the measurement is like basically it's whatever the quantum information that the results, right? So outcome of whatever the circuit that we are writing it. So we can see in the image on the right hand side. So this is like the line is each of the state transition. You can see it in the this is how the visualizing the quantum circuit. So we are going to see with the examples. So assume that qubits as wire. So each of these wire on the left hand side. So these are called as qubits, and horizontal represent the qubits flowing through the time from left to right. So each of these, if you flow here, so these are time differences, right? At the state, this is the time. Time has a vertical axis, and the horizontal one is like the state. And the gates as the operation. So each of these, whatever the square boxes, those are all the operations. So whatever the gates that we saw, right? So the previous one. So whatever the X naught or Hadamard or the C naught gate. So these are the operations. And the circuit depth is like more number of sequential layers that determine the execution time, and deeper circuit for more decoherence. So that the depth of the circuit, the time that it takes, so it transforms the data and provides us the better accurate results. So for example, a 2-qubit entanglement circuit uses Hadamard on qubit 0, followed by C naught between qubit 0 and 1, creating a Bell state in just 2 layers. So these are different concepts, like the Bell state is one of the concepts. By just putting these two operations on a 2-qubit, so we can achieve this. Okay, now we understood the concept what quantum computing is and quantum circuits are. So what are all the public cloud services available on quantum computing? Right, so we have a multiple cloud providers, public cloud services like AWS, Microsoft Azure, Google Cloud, IBM, Honeywell, Rigetti, Alibaba, and D-Wave, right? So they have their own quantum computing services just listed on here. AWS has a service called Bracket, which really helps us to access quantum hardwares like D-Wave, IonQ, and Rigetti. Again, AWS mostly they partner with some direct providers. So they provide a hardware and they bring in their layer on top of it and provide marketplace-based service. And they also provide open source quantum SDK for developing these quantum computing programs, algorithms, and machine learning models. And Microsoft Azure Quantum is there. They also provide multiple hardware options. And also they call it as QDK, Quantum Development Kit. And they also provide simulators, right? So we don't have to run the quantum simulators. We have to test our whatever the program that we have, run it on the simulator rather than running quantum machine, because before running on a quantum machine is too costly, and we're going to see why it is so costly. So rather we start with the simulations, and then once we are comfortable with all the optimizations and result, then go and run an actual quantum machine there. So similarly, Google Cloud offers Google Quantum AI, which uses a Sycamore processor, and they open sourced a framework called Cirq. And they also have quantum ML tools to run develop ML models and algorithms. And another pioneer in this is IBM. IBM Quantum, they also had open source Qiskit framework. They also provide in the cloud access to IBM quantum processors if you want to write and simulate models. And similarly, other providers like Honeywell, noticeable improvements from Honeywell side quantum solution. They have a trap time quantum hardware and HQC platform, high quantum computing platform. And Rigetti, they are also pioneer. They provide a service called Forest via AWS marketplace. They don't have a separate dedicated cloud, but they partner with AWS to provide the service. And they also have a proprietary Quill language and the quantum VM simulation and integrations with other AWS services if you have a other primary workload running on AWS. Alibaba provide the QCAS, quantum computing as a service, where it provides similar simulation algorithm development tools in their cloud. And D-Wave have a name called Leap. So they have quantum annealing, hybrid quantum classical workflows. So these are different options if you want to try. And since it's evolving and more innovations coming in, we are also going to see the quantumcircuits.com. So they provide a simulation where it directly feeds in quantum assembly language, QASM, not through Python. So they have the quantum assembly language. You can directly feed in and test the circuits that we are building. Okay, take that as no. So again, pardon for some people outside Tamil Nadu. Just wanted to make it more conversational. Just want to ask some trivia questions. So we know we use this selfie, right? So we take selfie more often every day with the cell phone. Can someone tell what is the Tamil equivalent name for selfie? Yeah, Tarpuhaipadam. Thanks for the nice guess, sir. So it's closer. Any other guesses? Because we use these words very often, but we don't. We miss sometimes to learn this in native language. So we just wanted to bring this relevant ones. Any other guesses? Then we'll share the answer.
சுய புகைப்படம்.
சுய புகைப்படம். Yeah, closer, ma'am. Closer. So let me share. So the equal word for selfie is Tami. So this also I learned it in one of the conference. So this is really interesting. And this one is easy. Artificial intelligence.
செயற்கை நுண்ணறிவு.
Yes, exactly. செயற்கை நுண்ணறிவு. And quantum. This is also interesting thing I learned recently.
நுண்துகள்.
Nuntugal. Yeah, it's like a molecule, right? So it's actually quantum. That is the exact word for quantum. Okay, so hope it's refreshes what we learned so far. So let's go into the Qiskit framework. So as for this demo, I actually used two frameworks. One is from the IBM, the other one is from Google. So let's learn about the Qiskit framework, which is IBM's open source quantum computing framework for building simulating quantum circuits. So first, for writing these environments, right, setting up the circuit. So we just have to start installing. It's again supports a Python node and other frameworks, but for our demo purpose, we'll use the quantum Python one. You have just install the dependencies there, which is a Qiskit framework SDK in our virtual environment. Then, if you want to run this on local simulation, we can run again this quantum again these simulations, right? So the simulators really helps us, and these frameworks really helps us to run the quantum circuits in our CPU hardware. So probably I'll add one more point, right? So we talked about CPU and even the classical computing, like how the recent LLM models. So we use ChatGPT, Gemini, and the Perplexity and everything, right? So those models run on these GPUs. So GPUs are like little scaled when NVIDIA launched this GPU, the intention was to provide the horsepower for parallel running online games. Right, so games need more processing power because it involves high quality graphics and multi-user interaction. So they came up with a GPU model where it has small multiple thousands of cores. So in the legacy microprocessors, right, CPU based one, so we'll have maximum 8 or 16 or 32. Even beyond now with the VLSI, so we have more cores inside it. But in the GPU, they even have thousands of cores. So you can imagine it needs a lot of horsepower. So it has to do a parallel processing. And that's how GPU was needed when they wanted to bring in more memory, the learned trained models with the natural language. So they need more horsepower to process whatever the input keywords or tokens that we give. So it has to predict and also do a research and get the result back, right? So similarly, the third type of hardware is where the quantum machines, where the quantum processors, which not only operates on 0 and 1, which understands the qubit concept and these entanglement superposition, right? So all these things they understand and process. Do you imagine this? So we are writing a program, we cannot run everything in a quantum, as I said earlier. So we need a simulator. So they thought this and created this simulator. So the program actually runs on the CPU. So because whatever laptop I'm using, it has a little bit of GPU, but it has more CPU based, right? So the simulators are capable of running these programs on the CPU. At the
Excuse me,
same time, yes, sir.
Sorry to disturb you, sir.
No.
Is it possible to run this Qiskit through Colab, Google Colab?
Yes, absolutely possible. So the code that I'm going to show, right, it actually has a Colab installed in my local laptop.
Thank you, sir. Thank you.
Yeah, welcome. At the same time, so if you don't want to run locally and you want to run this on the IBM cloud, right? So it also provides that. So you can select the target machine where you want to run this, right? So you can create a machine, simulator machine, and you can run either local or a target machine. And the core components, right? So they have a quantum circuit SDKs are there, so where we can build that and AR simulator. That's an AR simulator is one of the simulator runs on the Qiskit for testing and transpiler for optimization. So these are the different components. So the simple first quantum circuit Qiskit, right? So where you can see in the Python, just import this module. And so if you want to create a 2-qubit circuit, so simply create this quantum circuit object passing the qubit number there. And the operation, right, we need to perform. So we have the qubits created, and now we want to perform the operation to transform, right? So where the hard mod to Q0, the Q0 bit, right? So we just apply this hard mod gate to this Q1. And again, applying C0, so which is Q0 and controls Q1. So we can see the C0 for 2 qubits because we learned that the C0 is for 2 qubits. So we are passing which qubit we are doing this operation for. And finally, we are measuring the both qubits. So we applied 2 gates. One is hard mod and C0. And finally measuring what is the state of those 2 qubits and visualizing. So the good thing is that we have this Visual Studio Code with Python notebooks is what we are going to see. So they really help us to visualize. So we install these some of the libraries there. So they really helps us to understand the circuit for the program. And okay, so like how we said, right? So what it does is, so it creates a 2 quantum and 2 classical bits. So that's why we are passing 2 parameters. This particular object creation step creates 2 L. H0 applies the hard mod gate to qubit and creating the superposition. And CX1 entangles a qubit with controlled NOT operation. So first one do a superposition and second one is the entangled. So finally measuring collapses the quantum state to classical outcome. So because we cannot read the quantum it's too fast moving. So it actually collapses it and provides it to a classical outcome, and draw will generate a circular visual diagram. So how can we run this? So we created those 2 operations. So we choose a backend. So AR is the simulator. In the simulator, so we get a backend, just QASM simulator. Yeah, somebody has a question, please. Go ahead.
Ramakrishna sir, you have raised your hand. Any queries? Ramakrishna sir, you have raised your hand. I hope there is no queries, sir. You proceed, Siva sir.
Okay, yeah, thank you, ma'am. Okay, yeah, so we get a backend. So here is where we want to run it on a simulation. if you can pass this QASM simulator, which is set up locally or in the IBM cloud, or if you want to run it on a real quantum machine, so here you pass the backend, actual quantum machine. Then execute the circuit. So this creates a job, the execute operation with the whatever the quantum algorithm that we created, the circuit we created, and which backend we want to run on. And the shards is another parameter, right? 1024 shards is what we are passing to run it. And finally, we are retrieving the result from the job and getting the count and printing the count. So for output interpretation, right? For a Bell state, you will approximately see 50% of zeros and 50% of one outcome, demonstrating the perfect correlation from entanglement. So when we see when we run this correlation, if it both qubit matches, so probably it's a perfect match. If it's any difference there or some decimal coming in, probably the match is closer. Okay, so here I think just for another example, like for GHZ state, so here we are creating with 3 quantum bits. And with the hard mode on qubit 0, then C0 from Q0 to Q1 and Q0 to Q2, and measure and analyzing this, right? So this expected result should be like a 3 qubits, right? So 50% of the ones which 3 zeros and 50% with 111, demonstrating 3-way entanglement for all qubits. Okay, so let's quickly jump on to the demo. Okay, hope you're able to see now. So I set up this Python Jupyter notebook here. So where this again, the same thing, I downloaded this Qiskit from IBM GitHub open source framework, right? So we are going to see the same steps. What I did, I installed this Qiskit, so requirements, right? So these are the Python dependencies. You can see all these Jupyter notebook, Qiskit 0.38 version, and all other see the visualization. This really helps us to see the graphs, circuit graphs and everything, and all the dependencies. AR for simulator and matplotlib is for, again, for visualization. So the once we installed it, then we can see a similar one, right? So they try to import the simulator, creating the backend. So we are naming this as AR simulator. If there is an error, so just throw it, right? I'll just run this. So running this, respond back. So the simulator created successfully. The next step, creating the first quantum circuit, right? So like how we saw in the code, so we are creating 2-bit qubit 2 classical bit circuit, applying the hard mod gate for bit 0 and the CX0 for both of these from 0 to 1, 0 and 1, and measuring the both qubits. So this is the one. So you can see we applied a hard mod gate for quantum bit 0 and 1. We applied CX0, and we can see finally what is the state. Right, in state is 0 and 1. We can see this. And measuring the circuit and getting the count. So what is the state of it, right? So what are the counts, right? Where we mentioned the shards is 1024. And with the same simulator, we are running this. In this AR simulator, the counts are like for 1-1, the count is like 525 times the qubits were in this 1-1 state, and 499 times the qubits were in 0-0 state. And superposition right now, right? So we know that this hard mod gate actually creates the superposition. When we measure many times, we expect roughly the 50% of time the qubits will be in 0 and 50%, because that's a 2-state. So it's a probability we have. So we are going to measure this with one qubit, and we are going to apply hard mod gate and measuring this. And so now first time we ran, it's 0. Yeah. So we are not doing parallel operation. So mostly it is actually the 0. So H is the hard mod gate. M is the stage where we are actually measuring the qubit state. Now we are increasing the number of shards, the number of tries. So it's like from 1024 to 2048. And you can see the number of times, right? So the zeros is like 987 times and one is at 1061 times. So now entanglement. So we applied the CX naught between these two qubits, Q0 and Q1. So see the measurement comes out of concentrated on 00 and 11, right? Because it's a superposition and entanglement, right? So measure the same. For this, we use a parameterized circuits. We give a parameter as 0 and creating a circuit there and trying this and measuring. So by passing these bind parameters to each of these, so we can see each of these with the 1024 steps. We can see multiple operations there, so 3 times for each of these. So now, like the one more step is it also provides composing and combining these circuits with multiple layers, right? With one qubit, multiple layers. So layer 1 does 2 operations. So second one this SXK, and finally composing this. So this is the quantum bit and different operations we apply, and what is the final state here. So basically, see, this we applied multiple states and all those things, but where will it help really in a real world use case, right? Solving what problem this helps to solve. So I just want to show a real world use case. So the churn predictor, basically what it does is, I mean, in many of these industries, right? So customer churn is one of the ongoing problem. When we say churn, probably customer retainment, right? So, for example, take Amazon or Flipkart, a customer coming in and buying a product, and they don't come back again after some time, like, or even take other subscription like Netflix or Amazon Prime. So, what is the probability of customer are going to stay in this, right? So, because it's a recurring subscription for them, month on month, they have to make a payment, or people come back and buy some product in Amazon, and they get revenue. So what is the probability of customer they actually go out of their service or stop making payments or stop coming back, right? So that's what we are going to predict. It could be multiple reasons, right? So we buy a service, we pay a monthly service, and we decide, okay, New Year is coming, so I decide not to buy anything online because it's too much. I'm spending on unwanted unwanted things that are there, so I don't want to buy. So we decide, okay, we go to store and buy it, not order through online if you take that resolution. So how does system know that, right? So it actually learns from either through feedbacks or the way we come and order in the platform or the way we use it, or even how much. For example, I have a Netflix subscription, and if I'm trying to watch a movie and sometimes it keeps buffering, it's not coming, right, or it's failing out most of the time. Then I'll get frustrated and call their customer care. I paid the money, you're not providing the service. Then if I call a couple more times, same issue. If it's not stable, then I'll probably move out to some other company like Amazon Prime or Haji or Hotstar. So those are the input data that we feed to the system. Not only one customer, but for a lot of customers. Then it actually and also it actually it also collects other real time data, right? So this is the pattern for customers moving out of the service. So based on this, we actually pass these data in the regular CPU or GPU based algorithm. It takes a lot of time. With the data grows for like more than like 100,000, more than like a million or 10 million billion users. Then probably it takes a lot of time. But with quantum, it's to parallel operation to predict this. So similarly here, it is for demo purpose, just using one qubit there and passing a couple of parameters and run the circuit with the simulator and binding this with old versions and target. This is while calculating the real world probability. It uses the real world probability is like 80% churn, right? So that's where it it applies the shards with all the value here. And let's run this through. So with this real world data that we are passing, the probability is 0.8. The churn rate for this. So this is how we can implement, take a real world use case and we want to solve it. How can we apply these patterns? How do you want to transform the data and do multiple operations and predict the state? Any questions? Yes, Hamid.
Sir, good afternoon.
Yes, ma'am.
Sir, actually, this is a nice example. This churn prediction is what we usually learn in all our machine learning algorithms, all those things. Like the same thing now we are doing it in quantum computing. Like, why
Yes.
is that there's a need something called as quantum computing when we can do things? ML is emerging and we are doing everything in AI based, ML based algorithms. Like, how do you think this quantum will help us in solving the same thing?
Yes, ma'am.
All doubt I have.
No, ma'am. Absolutely very valid question. So I just took a very simple example to get the real world, but definitely this example, right? You don't need to go to quantum we have to spend so much money and waste energy to get this on. But the quantum is designed for very for example, if you want to solve a problem, I think recently I studied. So one of the biggest puzzle of in the rocket science, right? The NASA, they actually have to do it for many years. This quantum circuit was able to solve this in a matter of minutes. So that's where these will use with the complex mathematical computation, with sending satellites and those areas, right? It really helps to solve them. But this churn prediction, definitely we don't need to use quantum. Rather use a real regular computing with ML models, right? With predictions. Hope that clarifies.
Thank you, sir.
Yeah, no problem. And also, this really helps if you want to do a stock prediction, and even that we can do it with ML model, but with the choice of the amount of data that we want to do. Right, so that's what. For example, if you want to predict the weather based on last 200 years of weather data, right, every hour wise, probably that might be a huge volume, and probably machine learning models with the GPU and CPU and takes maybe a few hours, but probably this can take a few seconds. So it's a choice that we make and the time that we want to solve the problem. So again, just to icebreaker, just to give a couple more interesting facts. So number of qubits that could represent more than all atoms in the observable universe. So we saw the power of qubits, right? Instead of 0 and 1, we can have multiple qubits. So probably if you give an example in the classical computer, right? So now it can address memory up to 64 bits, right? So we by earlier processors used to support up to 32. Now we go up to 64 bits. Right, so that's how it addresses memory of whatever size we want currently, and it's able to solve our regular day-to-day problems at least in a couple of seconds in our computer, like x86 processor or AMD or the cloud computing. But if you look at it in the qubits, where it can have a number of bits there, how many qubits do you think to represent the entire atoms in the entire universe? Any guesses? Any guess numbers? How many qubits? Okay, so I'll share this. So there's 360. So if we create a circuit and use the 360 qubits and do the operation, so this is equivalent of, or you can see the atoms in the observable universe. So you can see how much coverage it has and it can do operation. Okay, the second one. So we talked about the simulators and the cost about running these in the actual quantum machine, right? So what is the temperature at most quantum computers need to be kept? Can you guess what would be the temperature if you run a data center and want to set up a quantum machine there? And what is the temperature we should maintain to run this? Any guesses on the temperature? We know it's like in the regular data center recently, right? So Microsoft, Satya Nadella met our honorable Prime Minister, and they promised to set up data centers this year, right? So they actually maintain these power coolers, air coolers, and burn, and also they have to take care of these carbon emission and all those things, right? So, but imagine that's for regular CPU or GPU based data center. But what about quantum processors? So they have to maintain a negative 273 degrees centigrade. So mostly their data center should be in the North Pole, where Antarctica or Arctic or Alaska kind of places where heavy snow and the negative temperatures are there. You can imagine. So this has to do a lot of compute, and it always be like so warm, right? So that's where they need to run it in negative 273 degrees centigrade. So that's why to run this, you can imagine the amount that they spend, and if they have to run it here, the amount of cooling that they have to use, and if you run a data center for a simple data center, they can run thousands of villages, give power electricity to thousands of villages. Okay, so the last one, the Neurona one is the latest invention from the Microsoft, right? So they introduced this processor. When was the first experimental demonstration of working quantum computer came? This is the year. First one was in 1998. So this is the first experimental demonstration they did for the quantum computer. Okay, so good. I think hope you learned something on that Qiskit from IBM. So you can try with you can download the code and try your own algorithms there. So now let's quickly try about the Cirq framework from Google's programming framework. So designed for NIST algorithm for fine-grained circuit control. This is another framework. Yeah, there's a question.
Sir,
Yes, sir.
can we use the graph theory or hypergraphs to represent the quantum particles? I mean, I'm talking about mathematical models, sir.
Yes. I can imagine. So we can use, but the thing is, but it's not going to have a more dynamic in nature, right? So graphs will have nodes in relationship. So if your state transition, if a node is going to change it into multiple phases so frequently, then definitely quantum circuit can solve. Right, but regular, if you look at, so it would be mostly like either the node can be transformed into another different node with the kind of relationship it has, right? Nodes and relationship. So I feel that regular graph, the regular our classical computing through CPU or GPU can solve this quantum.
Yeah.
That's my point of view. Thank you. So let's get into there. So similar to this, right? So what we saw the quiz, so we have to install this Cirq SDK there with the tools. It has a lightweight setup there for immediate coding. You can use the cloud-based Jupyter notebooks provided by Google Cloud, which doesn't need any local setup, so we can directly run from a browser. We don't have VS Code or don't want to write it locally. And the core concept, right? Again, it will have a qubit circuit moments like gate layers to perform the operations. And so we'll have a more explicit control over timing and scheduling. So similar to this, the Bell state, right? So where it defined the number of qubits with the range of 2, building the circuit. And you can see while building the circuit itself, we perform these operations like Adamant or C0, and finally measuring the results. So performing the same, it's a kind of different way of representing it here. And here the simulator again, we can create the simulator module and also run the sample one with the repetitions where we have shots in the other framework. Here they call it as repetitions. And finally, analyzing the results, so they provide the histogram here. So for the perfect entanglement, so roughly like 500 measurements of 0, 0 and 500 of 1, 1, right? So similarly for binary 3, we'll have 1,000 repetitions. So for hands-on, the teleportation exercise, right? So create the circuit with this 2 states, and LIS operations where perform this, finally measuring this, and finally doing these corrections that we can do with classical controls and all, with applying X and Y gates. So we saw 2 frameworks, right? So even here, I'll just quickly run through this Cirq framework. I just have a demo set up for that as well. here. So this will have a parameterized circuit and creating a simulator here and matching an 80% churn predictability. So this also gives the predictability of like 0.80%, which is like this is the rate it predicts it. Similarly, this is also the open source framework you can direct download and play around with this local simulator. Going back to the presentation there. So final part is right. So just we saw two frameworks, so a comparison of those, which one is better for what use cases, right? So the Qiskit framework, so which is the IBM hardware that integrate with IBM systems and giving a priority access if you directly use IBM's one. And it has an extensive library for optimization and the chemistry and machine learning. They also support ML models there. And learning resources, they have a good tutorial, even the GitHub. A lot of examples and YouTube videos, people start exploring this. They also have a lot of books and community support as well. So if you raise queries and there is a good support available. And visualization also, they have a superior drawing and result piloting tools. We just saw that in the VS Code itself. Where at the Google side, right? So they have access to this Sycamore, that's quantum machines that Google has. And also they will provide access to, of course, for the future Google quantum processor that they identify. And as you guys know, there is a separate research wing from Google side. They do extensive research on inventing this circuit movement. So we find and control with gate scheduling and parallelism, right? So the earlier side, other side, IBM side, we didn't have a gate scheduling. So we directly applied there, but here they provide a scheduling at what time you want to apply the gate, so which will have a control and also have a parallel operations. Again, lightweight, flexible, open source model. So these are optimized for near-term quantum algorithms. So that is another concept they support this. So just advantages, advanced tips, right? So we write this and we saw that there is an optimization. So which the transpiler is the module, that a framework which the Qiskit offers to have a reduced gate count and adapt circuits to hardware constraints. So we want to use less amount of computer horsepower to run this. So this transpiler really helps us. So we can even pass the optimization level so that it can provide maximum optimization, so reduce the amount of hardware that it uses, and also reduce the error rate and have a execution time, right? Improve the performance. And parameterized circuit, we saw that passing the parameter is one of the options there, where it helps us in terms of while running machine learning algorithms. It really helps us to tune it in different angles and also train it iteratively on when to perform what operation based on the data. And also we can introduce noise simulation for a real world use case. So how the model and the machine behaves when there's an external noise or the unwanted data that we have in the model. So this also really help in getting those cured. So finally, resources and next steps. So we have the documentation. I can go to directqiskit.org for API references if you want to leverage that. And the Google's path for this Cirq, and both offers Jupyter Notebook. We saw that. Untitled Performs, they have a cloud-based quantum computing environment, both of them. And also local simulators we just saw for offline use. And the project ideas, so they have solve optimization problems and graphs. We just talked about it. Ishwar asked about the graphs. So we can have calculate molecular ground state energies is one of the things. And Groover's algorithm is also the quantum database search. So these are some of the project ideas we can try it out. So that's pretty much it. I just wanted to conclude with the key takeaways where these quantum circuits are the universal language for quantum computers. And these are the clear Qiskit and Cirq are the leading open source cutting edge quantum algorithms to run on the hardware. And we can try downloading the frameworks and try your own. And so we are here to help if you need any support needed for if you want to try anything, or if you want to solve any real problem, or architecture discussions, or debugging assistance, so feel free to reach us. Thank you so much, ma'am, for the opportunity, and thanks everyone for being a wonderful audience. So
Thank you.
please
Thank you.
feel free to reach out. This is my LinkedIn QR code. Please do connect, and thanks again.